Today we're going to move into quantum mechanics. We're going to look at something more complex than we've done before. We're going to look at some more emergent properties as we go to a more complex situation. But here we're going to try and do the, as it were, physics at one go, because quantum mechanics is basically the foundation and fundamentals of physics. And in particular, one equation is the Dirac equation. If we can get the Dirac equation, which is the equation relating to fermions, the most fundamental object in physics, and their interactions, then we've got a basis for physics. So at its deepest level, physics is only about fermions, or their interactions. Bosons, the other kind of particles, emerge from the interactions of fermions. They're not a separate concept. If we can get an equation for the fermion, and we have one because we got the Dirac equation, then we will understand a great deal of physics. And if we can understand that on the basis of our algebraic structure, then we can use our algebraic structure to understand a lot of physics. Now, we've already derived a version of the Dirac equation from the algebra, from the fundamental symmetries of the parameter group. What we want to do now is to get the same version of that equation using conventional Dirac equation, using conventional quantum mechanics, go from that and show how this new algebraic version of it can be derived in that way as well. Now, we start with the Schrödinger equation, which we won't write down because we don't need to for this purpose. But the Schrödinger equation is the one that many people use for quantum mechanics, and it's a very powerful and useful equation. This is a non-relativistic equation, and it has a differential squared with respect to space on one side of the equation, and a differential linear with respect to time on the other. So it's not, the two parts cannot be made relativistic because you need either both squared or both linear. And when Schrödinger was faced with that, he realized what he could do was to create an equation which he got from Einstein's energy momentum mass equation, E squared minus P squared minus M squared equals 0, or E squared minus P squared C squared minus M squared C to the fourth equals 0. And he realized he could get an equation from that, and he did get such an equation. He didn't publish it, but he got such an equation. And it's now called the Klein-Gordon equation, and that equation has a differential squared in space and a differential squared in time. But he found he couldn't use it to describe fermions such as electrons. It didn't have the right mathematical properties to describe fermions. What you need for fermions is a linear equation in space and time. So he got a relativistic equation, but it wasn't the one he needed for describing electrons or other fermions. So we need a first order equation in the two variables. And the way you can do that is by square rooting the second order equation. Now, if you've got three terms like E squared minus P squared minus M squared, and you want to reduce to something equivalent to E, P and M, there is a way of doing it if you use algebraic operators. Because if you take, for example, a plus b all squared, you get a squared plus b squared plus 2ab. But if you arrange it so the algebraic operators there are algebraic operators in front of a and b, such that when you square it, that they cancel the cross terms ab and ba, because they're anti-commutative. If you choose anti-commutative operators, you can do it. So if you're careful in your selection of anti-commutative operators, you can linearize the equation without increasing the number of terms or decreasing them. And Dirac managed to do that. Now, because of the time when this happened, Dirac used matrices. That was the most favored method at the time, to use matrices. He used matrices because matrices are anti-commuting, and he was able to use 4x4 matrices as his operators. So in front of his energy, momentum, mass terms, he had 4x4 operators which were matrices. And this equation that he derived worked spectacularly, and it's one of the great discoveries of 20th century physics. And one of its big achievements was that it was able to derive the strange property of half-integral spin for the electron from first principles, direct from the equation without any assumption. Previously, you had to assume it. Of course, half-integral spin means that the electron has to go twice round its cycle to get back to where it started. This is what one form of the equation looks like. And we have gammas, and those are the matrices. Gamma mu, there's 4 different matrices. D mu is the differentials with respect to space, 3 of them, and time. So that's 4 differentials, 4 gamma matrices. And then he has a mass term, and then he has his wave function. And this is writing it out in full. And that equals 0. That's not the only form of the equation. There is another form which he also used, which has different matrices, but related to these by an algebraic transformation. We'll actually mention those later. Now, these gamma terms are matrices, and they're mutually anti-commutative. And they're all either square roots of 1 or minus 1. So we recognize the Clifford algebra aspect to this, as Dirac himself did. He realized that Clifford algebra could be used for this. But he didn't write Clifford algebra as we would in terms of algebraic operators such as quaternions. He used matrices. And here, instead of having a square root of 1, he has a square root of the identity matrix, a 4 by 4 matrix with 1s along its diagonal. And gamma 1, 2 and 3 are square roots of minus 1, and in fact minus the identity matrix. And then these 3, as you can see, they're related to dx, dy and dz, that should say dz. Those 3 are actually comprise a vector quantity of some sort, to which you can give the generic symbol gamma. Now, this algebra with the 4 lots of gamma is closed, but only if you add a 5th term, which is called gamma 5, which doesn't appear in the equation. So you need 5 objects to create your algebra and make it a closed algebra, a true algebra. And this gamma 5 is a square root of I, like gamma 0, and it's anti-commutative to all the others. So we've got the 3 vector ones which are square roots of minus 1, and the 2 others which are square roots of 1, and they're all anti-commutative with each other. Now, we can treat these gammas also as generators of a group of order 64. And we're familiar with groups of order 64 because we've done that since the 2nd lecture onwards. We've been talking about groups of order 64 made of 5 generators. Now, the composition of these matrices isn't unique. There isn't only one way of doing them. But this is the classic way in which one normally does them, though other matrices are used for special purposes. So you can construct them out of Pauli 2 by 2 matrices. So if the I is a 2 by 2 with 1 along the diagonal, so you've got 2 times 2, and this becomes a 4 by 4 altogether. And so the other 3 gamma matrices are made up out of the sigma matrices, and gamma 5 is constructed in that way. And so that's the classic way of doing it. And you can expand those. I haven't put gamma 5 on here, but here you can see gamma 1, gamma 2, gamma 3, gamma 0, and this is the identity matrix with just 1s along the diagonal. And one thing I want to point out while I'm here is that these here, notice that gamma 1, gamma 2 and gamma 3, which are parts of a vector, they don't look all that much alike. See, that one has got real terms and that one's got imaginary terms. And this one over here is skewed with respect to these 2. So even though they're a sort of symmetric, rotation symmetric group of 3, they in fact don't look symmetric when you write down the matrices. Now, if we bundle all those together and put them back into the equation as we had it, let's look back at the equation for a moment. Imagine reconstructing this with 4 matrices there. Reconstruct it to see what it would look like when we put everything together. We would get that. This is what the operator would look like when we put all the matrices together. Now, what Dirac saw was that if you had a 4x4 matrix, then this wave function was no longer describable by a single term. You had to have 4 terms to make the equation work. And this quantity is called a spinor. It's a column vector with 4 components, and it's called a spinor because it generates the spin properties. And he said that these 4 represented particle and antiparticle, spin up and spin down. That's what happened when he investigated the equation further. Now, I can't find anywhere where Dirac has actually investigated the Clifford algebra aspect of this. He seems to have been happy with the matrices, been able to manipulate them, and been able to do the calculations he wanted. But as I mentioned earlier, they form a group of order 64, and that's very significant to us because we've seen that structure before. And you have to, of course, include the identity matrix and real and complex versions to get the 64. What you can do is to use the set of 4x4 matrices and you can derive all the variant possible forms in a special way. You can use 2 sets of Pauli matrices. I've written the one set in blue and one set in red. Now these 2, if you imagine these 2 are commutative with each other, commutative quantities basically don't know that things that they're commutative with exist. They carry on regardless of things they're commutative with. So the sigmas are anti-commutative with each other. The blue ones are commutative with the red ones, but each are anti-commutative with each other. And if we remember from lecture 2, what happens with a group of orders 64 with 5 generating elements made out of 2 lots of 3, it ends up looking something like that. And those are 2 versions of it. You could, of course, have pluses and minuses here. That doesn't matter. And what we see here, once again, is the classic case of a broken symmetry. The blue ones here, the small sigmas, are all symmetric because they have I and big sigma 1 in front of them, or multiplied by them. But otherwise, they only vary through the sigmas. So those are rotation symmetric. But if you look at the big ones, the red ones, then you see that they are multiplied by different objects in each case. And therefore, their rotation non-symmetric, asymmetric. So if we multiply all those out, we'd find we got exactly gamma naught to gamma 5. And in fact, all the different variations of those sigmas will produce all the different variations of these. And I've never seen that in any textbook. So it's not a widely known concept. But the thing that matters to us now is that these things here, which we've seen before in lecture 2, these things here are symmetric, isomorphic, I should say, to the 2 sets of vector units, I, j, k, blue and red. Or, if you like, complexified quaternions. And we've seen that structure before. Now, even using the Pauli algebras, we can see that if we break this symmetry, then we will have the same structure as we had for the vector quantities. Let's go back to the equation. I'm going to do something to this equation which looks like a trivial operation, but it has very profound consequences. This is the equation, that equals naught. What we're going to do is multiply it by minus I gamma 5 from the front. It's not going to make any difference to it being 0 when we work it out. So this is what we get. Now let's use the double Pauli algebra that we have. And we've got sigma I sigma 2i in front, and that's what it would now look like. And when we multiply it out, it looks like that. And you can see why I use two different versions of the sigmas. If you look back at those, really, effectively, if we ignore the minus signs, that one multiplied by sigma 2 in front is going to look like this one. And so the difference between this equation and that one, the original one, is that now we have a sigma term in front of the m, which we didn't have before. And so what we've got now is a structure in which all the sigmas are present, all the capital sigmas, all the small sigmas are present. The whole of the 5 generators are present inside the equation, which we did not have before. This is a new degree of symmetry in the equation, meaning that the equation effectively has a somewhat different physical meaning to what it had before, because now we're saying this is really the story of two spaces. We've got the two lots of sigmas and the other two lot of sigmas, but both lots of sigmas are in the equation. In other words, all the bases of the spaces are in that equation, and they weren't before. And of course, the physical meaning will become even more apparent if we replace those sigmas by I, j, and k. The double vector algebra. In fact, we will probably choose a vector quaternion algebra, which we know we can use, because that is equivalent. And that's because that has a specific physical meaning for us. And we will find out even more interesting results from this when we find out that not only are the gamma matrices, all these algebraic equivalents, within the operator, they're also within the wave function. But we've got to find that to be true. Let's now replace our gammas or our sigmas by those operators. Let's just go back to see what we're trying to replace. We're trying to replace these 5 or those 5 with operators like those. So that's gamma naught, these are gamma, and that's gamma 5. They have exactly the same mathematical properties. Now the equation will look like this, and we can gather the differentials in space together in that form. This is purely mathematical. We've not made any physical assumptions whatsoever for any of this development. Now what we're going to do is what is often done the first time you have such an equation. You try it on a free particle. A free particle wave function looks like this. There'll be some amplitude term, let's call it A, and then there'll be the exponential term, the wave part of it, giving the wave properties, e to the minus I, et minus p dot r. That's a standard expression for a free particle, a plane wave. And if we now substitute it into the equation we had, and then apply this differential to this object, the amplitude term remaining unchanged, the differentiating that e will give us this term in front. So that's what we will get. We will get that equation. And this is exactly the equation that we got directly from the parameter group. So now we are back to that point where we wanted to be. What we now see is that this is really, as we said on that occasion, the minimal statement of the variation of space and time within a structure from the minimal algebraic generators we could get from the parameter group. Now, if we look at the equation again, we've got to equate this to 0. Now, the exponential term can't be 0, that's a non-zero term. So this thing times a is going to be equal to 0. This we know to be a nilpotent, and therefore a must be made up from the thing that must make that 0 when we multiply it, which is itself. So we now know that a looks like that. And so the a must be identical to this. I'm now using my color coding again because I can. Or a scalar multiple of it. And the scalar multiple aspect is insignificant because we can eliminate that by normalization. It's important to mention here that because the p term is a multivariate vector, that's why it's bold. The bold blue term, it's representing all that space, all the blue space. These spin terms Often one writes sigma dot p or sigma dot del in the Dirac equation. In general, it doesn't matter whether we do. It doesn't matter whether we write sigma dot or just write p, because we can see that when we square it, we will get the same answer. Now, here's where we're going to make physical capital out of this, because the very important thing about this representation is that it's not just for a free particle. If you do Pauli exclusion for real particles, none of them are free. They're particles in atoms or molecules or something like that. They're not free particles. There's no such thing as a free particle, and Pauli exclusion, as we measure it and as we use it for various purposes, is not about free particles. So what we're saying is that though we can immediately see why it will work for a free particle, we want to see why it should also work for a non-free particle. Because essentially, calling that a nilpotent is saying that it's Pauli exclusive. You cannot have two wave functions entirely the same. If you do, the combination will be zero. So what we're saying is that this is now Pauli exclusion. Another thing we're saying is that for the first time, every time we write down a wave function in this algebraic structure, we will always know exactly what it looks like. It will not be a black box hidden behind a sign. We will have an explicit expression for it every time. And this means that it's not just a calculating device any longer, it's a piece of physics. Obviously, quantum mechanics isn't going to change in principle. It's still abstract, it's still probabilistic, but it's no longer arbitrary. And if I may put it this way, we need to think outside the black box. Now, the spinor properties of the algebra still hold, even if we don't use a matrix representation. The matrix representation is useful for getting us to the spinor properties, but it isn't exclusive to them. It still must be a spinor whether there's a matrix there or not. And psi is going to be a four-component spinor with Fermi and anti-Fermi and spin up, spin down. Now it's easy for us to identify these. We know that plus and minus IKE are the particle and antiparticle, and we know that plus and minus IP are the spin up and spin down. And so I can write it in that way. There are four terms abbreviated in that way. However, in reality, this is either a column vector or a row vector, normally a column vector. So that we should really write those in a column. In fact, we will do that on the next slide. So we write them down in a column. That's just an abbreviation with plus and minus. Now the signs are actually arbitrary. We could have called the particle minus and the antiparticle plus. It's an arbitrary decision. But we've got to make some convention, so if we choose a convention and stick with it, that would be the way we should proceed. And here, we've chosen the convention where that spin up particle, spin down particle, spin down antiparticle, spin up particle. Now once we've decided our convention, then the spin state of the particle, by which we mean the helicity, the handedness. Is it right-handed? Is it left-handed? Left-handed means it goes left-handed as in the direction of motion. Right-handed means it goes right-handed in the direction of motion. Mathematically, of course, whether it does physically or not is another question. If we do this, then IP over IK has the same helicity as that. It's the ratio of these two that determines the helicity. This one here is the opposite helicity. What we're saying here is that our convention is to say that that is the particle state we're talking about, the first term. The rest are the alternative variations on it, but the actual particle state is always written as the first term. So the first or lead term represents the particle as observed. All real fermions incorporate spin up and spin down at the same time, but they don't actually incorporate a real anti-fermion. Now, if we wanted to represent an anti-fermion spin down, then we would simply put that as the top term in the expression and then change the signs accordingly. Now let's go back to the conventional Dirac equation. And that you may remember what I was saying about the matrices, that they were not symmetric with respect to each other, even though they represented something symmetric in nature. And here we can see the result of that. If we look at this term here, minus d by dx plus id by dy appears in the equation, but I don't know of anywhere in nature where such a thing occurs. D by dx and d by dy are the same sort of thing in nature. They're not, one of them isn't real and the other imaginary. So that is not what happens in nature. Notice also we've got plus and minus d by dt, but they always have plus im. So the gamma matrices are not either all real or all complex, all imaginary. They don't have the same mathematical status. They're not symmetric. And the reason for that is that matrices are a two-dimensional algebra in effect, and we're trying to represent a three-dimensional algebra with a two-dimensional algebra, and that's where the distortion comes in. What we have done is undistort it. We've discussed this looking at the previous slide. So what we need to do now is to undistort the equation. Another aspect of the equation which is a problem is that, you see, we got 16 terms there, and we got 4 there, we got 64 terms. But 16 in the operator. So to do one operation we need 16 terms. I say this comes about because we haven't respected nature's choice of mathematics. That's what we've got to do. We know what nature's choice is if we follow what we did in lecture 4. Nature's choice is what we are doing here. The quaternion operators, if we choose nature's choice, let's call it that, will be a bit like extending complex numbers to 3 dimensions. And of course we know how valuable using complex numbers is, because we can separate 2 parts of an equation, the real part and the complex part, and get 2 bits of information. Here we can separate 3 parts and get 3 bits of information. And if you like, this is defragmenting the equation. And we've seen this kind of thing before when we've defragmented disks. So it's a bit of an analogy to that. So we've got 3 parts, we've got 3 bins, as it were, for our terms. So we've got the first term here, the k. Let's represent that by the blue there. So the k is the energy term, that will be the momentum term, and that will be the mass term. And we've separated them out into 3 bits, instead of the scrambled thing we had there, which was like the matrix equation. We can now write all the 4 terms out separately in this way. We've got an operator, we've got an amplitude term, of which this part is the phase factor. Now, I want you to look at that equation very carefully, because what you will see is that all the operators are identical. There's only one operator. We've reduced 16 terms to one operator. Here we've got 4 different phase factors going through all the variations of E and P. And here we got 4 different amplitudes, again going through E and P. And I'm going to do another trick here, a trick that makes a huge difference to making this an easy equation to use. We're going to remove the variation in the phase factor, because when you have to solve a Dirac equation, the first thing you've got to find is the phase factor. If you've got to find 4, that is infinitely more difficult than finding 1. So we're going to reduce those to 1 phase factor. However, we're going to transfer the variation in that onto the operator. Well, that's compressing it. You see, 1 phase factor now, 4 operators. That's the same as before, but that's now 4 different terms. That's 1 term. So imagine we're putting the plus and minus variations on these terms and taking them away from these on the phase factor. And the most convenient way to do this is to represent the first term by a row vector. So it would go out here with 4 different terms. The second term by a column vector, and the scalar product, as it were, becomes 0. And we have a single equation for the whole thing. We can show that that gives us very much stronger calculating power than we would otherwise have. Now, another key thing about this equation is that the operator and the amplitude actually look the same. They've got the same structure. They're a copy of each other. And if I can write d by dt as IE, or minus IE, using the old Schrödinger prescription, and the same for IP and the del term. So I can actually write the operator. That means an operator now. It doesn't mean a wave function. That's an operator. I'm just writing that in operator mode, E in operator mode. But it looks identical to the wave function, which is a key aspect to this concept. And what I want to point out here is how the sign changes, we have to do it from this one, the sign changes in T correspond with sign changes in E. So as I change the sign of T, I change the sign of E, which of course is Feynman's famous prescription of antiparticle going backwards in time, particles going forwards in time. You see it comes out of this quite naturally. And if we'd actually said, I'm going to sit down and write down a quantum mechanical equation from first principles, I think this might have been what we got, directly from the parameter group. So what we've done it by two methods. We've done it straight from the parameter group, and we've also done it by, as I say, reverse engineering from the various theories that we derived empirically and over a period of history, like relativity and quantum mechanics. Now, quite clearly, if we have this equation, this is the ordinary Einstein equation split up into these algebraic operators. We could have started from that and derived the Klein-Gordon equation that Schrödinger originally got and didn't feel he could use. Here we go, this is the Schrödinger equation. What we do is, instead of just quantizing one bracket, we quantize both. So we quantize that bracket and that bracket, so we got two differential operators operating on this wave function, which here we've used a free particle for convenience. And so this gives us the Klein-Gordon equation. So we can see that the Dirac equation and the Klein-Gordon equation are part of the same stable. They're not separate pieces of information, really. People often say the Klein-Gordon equation is for bosons, the Dirac equation for fermions. That isn't true. The Klein-Gordon equation is for bosons and fermions. It's for all particles. If we couldn't use the Klein-Gordon equation, we could never have worked out what those gamma operators were. That's how they were worked out, by using a combination of the Dirac and Klein-Gordon conditions. So a Klein-Gordon equation will lead to any particle, because you've got that phase factor with the squared operators working on it, and therefore you'll get E squared minus B squared minus M squared. However, the Dirac equation won't apply to a scalar wave function. It's got to have a wave function with like that, because it's only got one bracket producing that. Now we can actually do something even more than that. This is a kind of mathematics which has certain standard aspects. A more powerful version of it has been worked out by my friend Luke Kaufman from Chicago. And this is the use of commutators instead of differentials. So it's if you like, it's a discrete kind of differentiation. If you use, say, df by dt, now that should be total df by t, not partial. But I'll explain why we've used partial in a moment. That's total df by dt. You can replace that with the commutator between the function f and the Hamiltonian h of the system. And if you've got partial d, that should be f, partial df of a function by dx, you can replace it with that commutator instead. H equals E, it's the same as the Hamiltonian. In our terminology, we can write the Hamiltonian as E, or KE, or IKE. Now the reason why we allowed in this particular case to use partial df by dt is because we're going to assume that there's no significance in this expression we're going to develop of the velocity operator. If we had a velocity operator, we couldn't do that. We would have to use full df by dt. But in this case, we can use it. So taking the case where the velocity operators are not in evidence, we can use partial df by dt. Now the interesting thing about this is that the mass term, which is really only passive in quantum mechanics, it doesn't do anything, it's just there to fill in the gap. The mass term disappears. And the reason is that you take a commutator of a mass term, and because it's a scalar, it just zeros. So the whole mass term will zero in the differential operator. So a differential operator, which we're using a script D, will look like that. It won't have a mass term. But it doesn't disappear from the wave function, which here is reduced to an amplitude, there's no phase. This is a discrete differential, so there's no phase term, there's only an amplitude. If we write these expressions in that way, we can now just do a little bit of algebraic manipulation, and what we get is this expression, it works out to that. And when we choose psi to be a nilpotent wave function, then we will get an expression like that. And you can see that that's a kind of Dirac equation with no mass term. We can do plus and minus as well, because we can generalize to 4 states, and we get that. The pluses and minuses are switched around, but overall that doesn't matter. But there's no mass term in the operator when we do this discrete differential process. And the particular reason why that's important is because if we were doing a classical expression, we could do a classical expression. The classical expression would be that. That would be a classical expression. A quantum expression would multiply that by IH cross. Because when you do the quantum expression, you need IH cross in front. In this case, you don't. So you can switch between classical and quantum simply by multiplying the whole thing by IH cross at the beginning. And you don't need to have made that assumption from the start. It gives us a smooth transition between the two regions, but only for discrete differentiation. So you're saying if there's a discreteness in it, then it automatically transits to the quantum version. Another thing that we should mention is relevant to what we did in lecture 2, which was to talk about idempotence as well. Now many people claim that the wave function for the Dirac equation must be an idempotent. That is, an object which multiplies to itself, not an object which multiplies to 0. And we showed in the second lecture that a quantity j times that, as we see here, j times what we now call the wave function, would be idempotent and not nilpotent. Whereas 1 times that is nilpotent. So that's idempotent, that's nilpotent. But we can see by immediate inspection that these two equations are identical. The only thing different between them is that we've decided to include that j into the operator rather than the wave function. But otherwise the equations are absolutely identical. So we can write down an idempotent wave function if we want. We will find that in this theory the idempotents have a special meaning. We'll find that out in the next lecture. What's important about quantum mechanics is that we need to try every formalism that we can to find out as much information about the system as we can. We don't say, the wave function is idempotent, the wave function is nilpotent. No, we want to look at all the properties it has. And that's very important because different formalisms gives us different aspects of the physics. The idempotent, we will find, is related to vacuum. I'm really saying there, quantum mechanics isn't just a set of formalisms, it really is physics, and it's saying things that have got direct physical meaning. It's not just a set of black box calculations, as is often made out. But the nilpotent formalism is the most efficient, it's optimized. You couldn't get a more optimal version of quantum mechanics. By reducing to a single phase factor, we can massively reduce the calculations we have to do. Calculations which take pages. For example, the hydrogen atom in conventional theory can be done in a few lines using this method, as we'll see in the next lecture. The extra constraint of nilpotency forces on us an additional interpretation that we didn't have previously. It connects the fermion holistically to the rest of the universe. we can make a lot of the formal apparatus totally irrelevant once we realise this, because we can actually structure our quantum mechanics to give us more information with apparently less structure. And I've already mentioned briefly what nilpotency means. Let me talk about it a little more. Pauli exclusion. And of course, physicists like to say that Pauli exclusion is responsible for condensed matter physics. It's also responsible for chemistry and therefore ultimately for biology. It's a tremendously important thing. Pauli exclusion says no two fermions can have the same wave function. That's one expression for it. So a fermion with a wave function psi1 is automatically Pauli exclusive because the combination state it could make with another fermion of the same psi1, psi1 is 0. So really we're saying that if we do that, then we can't have psi1 equals another wave function of the same kind. And as I mentioned earlier, naturally occurring fermions are not free particles. They're bound, or they've got potentials which restrict them in some way or another. And so we redefine the operators E and P to include any number of field terms. For example, ID by dt, that's a Coulomb term, Coulomb potential, E phi. And P then would become, that's a vector potential. But we could have any form of potential, we could have any number of them. And we can redefine the E to not be just that, but to include that as well. But we can still write down a nilpotent operator as that, because we've got our three bins, I, J, and K. Obviously, if we had such a operator, including those things, then the E and P that we got as eigenvalues when we solve the equation would be a lot more complicated than just E and P. They would include a lot more terms. But they would still be separated by the three quaternion operators. And the phase factor would certainly not look like that. It would probably contain an exponential of some sort, but it wouldn't look like that. However, the system will always be constrained because we need to maintain Pauli exclusion at all times, free or interacting. What will happen is that this will give us unique coding, uniquely coded information on the system, whether or not we've got external field terms. This is what we do. This changes quantum mechanics. It's not a subject about equations any longer. We don't need to bother with equations. We can do it differently. We write an operator in that form. The E and P are now generic terms which involve differentials with potentials and whatever else they may have, covariant derivatives, whatever else they are, something or other representing E and P. And once we've defined that operator, then that's it. There's no further information that we can supply. That is the entire quantum mechanics for that system. The wave function and even the equation itself become redundant as independent sources. The wave function is simply the thing that emerges directly from that, once we've defined it as an operator. So the operator alone and uniquely, completely determines the phase factor, which will create a nilpotent amplitude. So if we've got an operator which we've defined, then we must find that phase factor, whatever it is, on which it can act, such that when we square it, we'll get 0. 0 amplitude. 0 amplitude squared, that is. 0. So we don't need a special quantum mechanical equation whatsoever. And even the spinor representation has no independent status, because the 4 terms are only 1 term and 3 variations, 3 sign variations, which are exactly the same in principle as the first term. So we don't need an operator with 16 terms and an amplitude with 4. We just need a single term. A single term. So we've reduced 64 down to 1, less than 2% of the original information we need to do it. We don't need an equation at all. It's amazing. So the most fundamental structure in physics as we know it is not an equation, but an expression linking the symmetric algebras of the 4 basic quantities. And that's what we would have expected. Where do equations come from? They don't. We don't need them fundamentally. We need this sort of expression. Now I want to talk a little bit about vacuum. because now we've got a real meaning for it, which we never had before. Vacuum is a very important term in quantum mechanics, but it's used in a way that doesn't state exactly what it is. Here we can say now exactly what we've got. And because we can state it in this way, that reduces the amount of work we need to do in quantum field theory, the next advanced step from quantum mechanics. We don't need any formal process called second quantization, which is a lot of trouble in quantum field theory. We don't need it because it's already done. It also invokes the idea that we've always had, that the fundamental totality must be zero. So we start by creating a fermion in some state. Whatever state it is, it doesn't matter. And that fermion will have its potentials. It will be interacting. It'll have a potential saying it's interacting that way, it's interacting that way, interacting that way. It doesn't have to be interacting with anything, it just has those potentials. And that will define that fermion, that status. Now imagine that fermion has been plucked out of absolutely nothing whatsoever. So you define what your fermion is, and then imagine that it can be plucked out of nothing. So to pluck it out of nothing, we've got to leave something behind, a sort of minus of that, a hole in the nothing, if you like. So that is what we call vacuum. That hole in the nothing is what vacuum is. You pluck the fermion out of nothing, and the hole left is vacuum. It's minus the fermion. So let's define the fermion wave function as psi f, and the vacuum wave function will be psi v, which equals minus psi f. Add them together, the superposition, 0. Multiply them together, the combination, 0. So we get totality 0, whichever way we do it. So the vacuum is the hole in the totality 0, produced by the creation of the fermion. And what that becomes is in fact the rest of the universe as seen by that fermion. Because to actually create those potentials in the fermion, you need all the other fermions and other things in the universe that will make those potentials possible. So the rest of the universe is that state of the universe which will allow the fermion to exist in the state that we've created it in. And that's what we need to create as the hole in the nothing. So we need to create the rest of the universe, or vacuum, simultaneously with the creation of a fermion. So again, we say zero totality. At the creation of each new fermion state, the universe divides into two. Local fermion state, non-local vacuum. This is a bit like the multiverse type version of quantum mechanics, where it splits into two at each time. And this concept is connected with the simultaneous existence of two vector spaces. So we got real vector space ijk and vacuum space with the other ijk. And the second one is derived from the mass of the charge units and the time units of the parameter group. And so because we've got two spaces, therefore we've got real space with the fermion, vacuum space with the vacuum, the rest of the universe, for that fermion. So in other words, a fermion constructs its own vacuum. So it has to construct the universe. So every time we change the fermion's properties, we change the universe to make it possible to exist. And the vacuum must be delocalized while the fermion is localized. And I'll say more about locality and non-locality in the next lecture. So the nilpotency defines the interaction between the local and the non-local. The fermion, vacuum. Real space, vacuum space. And the mechanism is the phase. And another way of describing Pauli exclusion is to say no two fermions can share the same vacuum. And now we can understand how they can connect. How do two fermions know that they're not the same? It's because the vacuums are spread out over all space, so they connect. The fermions don't connect, but the vacuums do. And here I'm saying that we can now completely separate out what we mean by local and what we mean by non-local. Local is this inside the bracket. If we multiply that out, we'll see it becomes Einstein's energy momentum equation. E squared minus p squared minus m squared equals 0. That's local. That's what local means. Local is all about Lorentz structure, Einstein structure, 4-vector, whatever you want to call it. Non-local is not like that at all. Non-local is everything outside that bracket. So any multiplication of that bracket by another, any addition of that bracket with another, is not a non-local operation. Squaring the wave function equating to 0 gives us back energy momentum, so that's the required Lorentzian structure. But once we do non-local processes like superposition and combination, we're going outside the bracket. I'm really just saying here that a single fermion can never be isolated. It must always be interacting. It's got to construct a space so that its vacuum isn't localized. To construct the fermion, we have to construct the rest of its space. So we need a dispersed vacuum for a point like fermion. Vacuum is, of course, non-local. It's like if we want to define a point, we can either define the point or we can define everything that isn't the point. And one is the point and the other is vacuum. Now this is the other way of expressing Pauli exclusion. This is the standard way. You take asymmetric wave function, psi1, psi2 minus psi2, psi1. And what you say is that if that's anti-symmetric, like if the reverse, psi2, psi1 minus psi1, psi2 is the negative of that, that's anti-symmetric, it's a bit like anti-commutative, then that is defines Pauli exclusion, because then one can write down matrices which will zero the two identical ones. So we can do that in this as well. I'm just working it out there. And you can see that the product eventually just works out to this. In principle, that's just a multiplier. We don't need to bother with that. The key information is P1 cross P2, and that's the only term that's left after you've done that operation. So in other words, this certainly is anti-symmetric because cross products are. However, it does give us something very, very significant here, which is very, very bizarre when you first think about it. What it's telling us that we wouldn't know that psi1 and psi2 were different at all if the instantaneous direction of the spin vector of each wasn't different. So the only way we can tell those two wave functions apart is by the instantaneous direction of the spin vector. Absolutely remarkable fact. In other words, all the information about the wave function is in the direction, instantaneous, of the spin vector, and nothing else. And the instantaneous correlation, well, we can think of another way where that can happen. Of course, we can use projective geometry, and we can project a plane onto any direction of a line. So all the planes must intersect. And those intersecting planes is what creates Euclidean space. I also think that one would say from this that the instantaneous collection of spin axes is not repeatable. It will give a unique direction for time as well, and also for energy. So you will get fermionic whirl lines will also be unique. And just going back to ordinary physics for a moment, if you've got a system with interacting momenta, P1 and P2, and there's some sort of interaction between them, then whatever happens, you don't get as much as you started out with, there's less. That also gives us a direction for time. I'm also saying here that the natural structure of the nilpotent is thermodynamic, and also that the formation of any new state is determined by the nature of all of the nilpotent states, and it's a creation event within a unique birth ordering. Each creation event will change all existing states to some degree. So we've now got 5 meanings for this expression. We've got special relativity, we've got the Klein-Gordon equation, the Dirac equation, we've got Pauli exclusion, and we've got a thermodynamic concept as well. These sort of multiple meanings, which also occur for the red K, I, and J, are characteristic of a theory in which duality is so prominent. Another way of looking at Pauli exclusion is to say that the phase factors of all fermion wave functions are unique, which means that the E and P values are also unique, and this is where we can use our dual spaces. These carry the entire information of physics. The first is rotationally symmetric, the second rotationally asymmetric, not anti-symmetric. So the first is real space and the space of measurement, the second the vacuum space. And this is, we've got 2 versions of Pauli exclusion, one from that and one from that. These are dual in all respects. The vacuum space nilpotency is nilpotency. Vacuum space Pauli exclusion is due to nilpotency. The real space Pauli exclusion is due to antisymmetric wave functions. Yeah, I'm just saying on this occasion that we can go back to our concept of angular momentum, that the EP and M structure, the nilpotent structure, is an angular momentum operator. And the P contains all the information, or the EP and M together contain the information, whichever. And here, you can imagine representing the P, the unique direction of P on three axes, P1, P2, P3. But you could also imagine it on EP and M axes. So you can imagine that there's a unique version of some vector which is created by EP and M, or IK and J, the red IK and J. And if you did that, then you would see that you can't have fermions with zero mass, because they would all be along the same direction, and you've got to be all different directions. They'll all be along the line E equals P, they're all along 45 degrees. And you couldn't have them, even if they were massless, you couldn't have them with the same helicity. And also, you can't have negative mass, because again, the negative mass ones would be on the same direction, but on the other side of the axis, on the other side of the origin. Very briefly here, I'm going to just say this is a purely operational thing that we need to do. If you're going to do quantum mechanics with something like that, you need to show that it has an inverse, and that it also that you can multiply it by some sort of conjugate to create a scalar value. Here we multiply it by the complex quaternion conjugate. The extra quaternion, not just complex conjugate, complex quaternion is because we've already pre-multiplied this by quaternion. So this is what we do, and this object here can be seen as the reciprocal of that. We will need that for, I think, lecture 7. We don't need that today though. And I'm saying that we will also be able to show that we get transition to a quantum field theory. Where I think that happens is when we say, let's forget about the equation, let's concentrate on Pauli exclusion. And when we say that all fermion wave functions are Pauli exclusive, then we can actually develop immediately a quantum field theory without requiring all the apparatus that we normally need. I'm not going to dwell on this because this is a routine calculation. I'm just showing that you can do the routine spin calculation. This will be available afterwards on the slides on the script, showing how you get spin half. That's a routine calculation. Again, this is another routine calculation, helicity, that if you have a massless particle, you get two helicity states. You can't have both left-handed and right-handed massless fermions. Only one of them can be massless, the left-handed one. If you had a fermion that was massless, which of course don't exist, but if you did, then the wave function for the fermion with the left-handed spin and right-handed spin would be identical, and therefore excluded by Pauli exclusion, and you can't have it. So you only have left-handed fermions or right-handed antifermions. Yeah, that's part of that demonstration. And here, I'm also saying, this is for future reference, if we have, if we try to use polar coordinates to talk about point sources, we need to use polar coordinates. We need to use a mathematical prescription to rewrite our equation in polar coordinates. Dirac did this for us because he wrote an expression looking like that, which we can insert into where the del operator normally is. We have to make the spin explicit here because we can't use multivariate vectors in this instance. And there's a very key result comes from this, that all I've done here is use Dirac's prescription for changing del to polar coordinates. But once I've done that, I realise that if I'm serious about having a point source somewhere, I can't get a nilpotent solution if I don't have, because we will get 1 over r squared terms will emerge unless there's a 1 over r in there. So simply writing that out in that way means I must have a 1 over r in that expression. And all the known forces have one. Gravity and electricity, it's the main expression. Strong force is the one-gluon exchange, the weak field, hypercharge, and the B0 gauge field. So each has a Coulomb term. And that's simply spherical symmetry because you can't get nilpotency otherwise. Again, this is a calculation which is standard. I'm not going to go into any detail on it. This is a calculation Dirac set up a velocity equation which Schrödinger solved, and he got an interesting solution. If you can write a velocity operator, you can rewrite your gamma matrices, gamma times gamma naught, you call alpha. So this is gamma times gamma naught, we call it alpha, and if you write down a velocity operator for the free particle, you can get an expression that's called C alpha, which is very interesting because when you solve the equation, you get a peculiar term that it doesn't have a classical analog. So you get the equation of motion for the Dirac equation. Schrödinger did this and he got this odd term here. And what he saw was that it was a kind of switching between the four components of the Dirac spinner. It was called Zitterbewegung. We still use the German word because it means jittery motion, but it's a very special jittery motion. A fermion actually propagates along the light cone. It only ever travels at the speed of light. Remarkable to think that a fermion only ever travels at the speed of light. It just switches between vacuum and real state, vacuum, real state, vacuum and real state. And that's a standard result, but we need to show that it's possible. We can see it as an intrinsic aspect to defining a point singularity through the nilpotent structure. And I will draw your attention again to the Berry phase, a multiple connected space. And the various versions of Berry phase that we can do. In each case, we can interpret the Berry phase as being due to this creation of a point singularity. The electron is like in its own multiply connected space. I think I've already mentioned this before. And that's why it becomes a spin half particle, because it has to go round twice because it's in its own multiply connected space. This is the very last thing I'm going to do. So this is CPT symmetry. The three transformations that you can do, the three fundamental transformations, you can change parity, which change the spatial coordinates, time reversal, change the time coordinates, charge conjugation, changing space and time coordinates together, which is effectively reversing particle and antiparticle. And we can do them by using operators I, K and J, naturally become P, T and C operators in this system. And so you can see that's a parity transformation. The momentum or space is changed. That's the time reversal one. The energy is changed, and that's charge conjugation. Both of them are changed. We can see how all of them together create an identity. So it's called the CPT theorem. If you do all three transformations, you get back where you started. CPT theorem is a combination of relativity and causality. Causality means adding the mass term in effect to the energy and momentum. Relativity says the square of that is a invariant. When you add the mass term, then you include causality. So you need all three terms for relativity and causality. If you want to do it in terms of time and space, you can do it into that term, and then you need the proper time, tau. Okay, thank you. Yeah, thank you.